Hey everyone, in this video I'm going to introduce one-dimensional motion under constant acceleration. So as the name suggests, one-dimensional motion means objects which are only moving in one dimension, only in the x direction or the y direction and not both directions together. Constant acceleration means the acceleration of all these objects is going to be constant. So that doesn't mean anything about the velocity and the position, it just means that the acceleration itself is going to be constant. Under this set of assumptions, we're going to derive something called the kinematic equations. So kinematic here, it doesn't really matter that you know what it means. What it means is how objects move, not why they move. Why they move is a dynamical question, and that's going to be solved by Newton's second law. Right now, we're only talking about how they move if they have constant acceleration. So these two equations right here are what I'm going to derive in this video.
Alright, so just to be clear, what I want to assume is that I have an object which is restricted to move in only one dimension, and that the object has constant acceleration. And what I want to find out is what is the position and velocity of this object as a function of time. So normally when you study physics and the motion of objects, you want some physical concept. You want to say, oh, I have a force, or I have an energy, or I have some kind of motion in order to determine how an object moves. Actually, in this case, the only thing we're going to use is calculus. So recall that just the definition of acceleration is the derivative of the velocity with respect to time. In this case, remember that I'm thinking of these as both only being in one direction. So that's the acceleration in the x direction and the velocity in the x direction. Well, just based on this definition, I can integrate this equation with respect to time. The next step is, of course, I got to put limits on my integral, but I want to work on this side of the equation first a little bit. See, I've got a dvx dt times a dt, which I've then integrated. Well, that dt and that dt are going to cancel because they're one's in the numerator and one's in the denominator, so I can just rewrite that side of the equation as an integral over dvx. Okay, so now let me put in some limits. Normally what we say is the initial position is t equals 0, so the time integral is going to go from 0 up to some time t. And the velocity integral over here is going to go from some initial velocity, we call it v0 in the x direction because I'm talking about the x direction here, up to some v final in the x direction. Typically we just call that vx. In fact, we'll often call that Vx of t because the time at which this final velocity occurs is the same time over here. So whatever time I put here is the same time that ends up here. So that's why this is that functional form Vx at time t. Okay, so now we can actually do this integral. Look on this side of the equation. This ax, that's a constant. That's part of the constant acceleration assumptions that go into this. If you integrate a constant, you just get the constant times the variable you're integrating over. So that side of the equation is just axt evaluated at the upper and lower limits of 0 and t. The other side of the equation, this is just like integrating a constant 1 over dvx, where you just get the constant 1 times vx with the upper and lower limits of v0x and vx of t. Okay, so now we can put in these limits. As you can see, that's pretty easy because this is evaluated at t. Evaluate this at 0, that goes away. Evaluate this at vx of t, you just get vx of t, and evaluate this at v0x, you just get v0x. And that looks like that. So now I'll just do a simple rearrangement to get the most common form of the kinematic equations, which is that. So given any acceleration in the x direction, an initial velocity, and a time, I can tell you what the velocity is going to be at that time. In fact, I can just plug in any old time I want, and if I have the acceleration and the initial velocity, I can tell you what the velocity is at that time. Okay, cool. So that's the first of the kinematic equations. That tells me what the velocity is as a function of time. So I've got this part taken care of. Now I want to know what the position is as a function of time. Again, I'm just going to go back and do some calculus. The definition of the velocity in the x direction is the derivative of the position in the x direction by the time, and so I'm going to start with the same basic process that I used up here, except that now this vx is going to be the vx over here because this is changing in time and this is how it's changing. That's a little bit different than up here when I had this side be constant. So the first step is to just integrate with respect to time. I've put Vx of t in here instead of just Vx to remind us that we're going to need to put this in eventually. And I've got the same thing happening over here, dx dt times a dt and then integrated, so I'm going to cancel out those two dt's to just get an integral over x. And I'm going to set the limits again. On this side, again, dt is just going from 0 up to t. My x position is going to go from whatever the initial x is, let's call it x0, and it'll go up to some final position, and let's call that x as a function of t. Because again, it's just going to match whatever the time is that I put in here. So to remind myself that this position will depend on the time, I'm going to write x of t. So now we have the left side and the right side of the equation. The right side up here is exactly like the right side happened up here, so I'm just going to fill that part in. I get x evaluated at the lower limit of the initial position and the upper limit of the position at whatever time I pick. And that just gets me x of t minus x naught. For this side, I got to be a little bit more careful because I have to plug this thing in, so let me just do that. Okay, so there's two terms in this integral. The first one is axt, linear in t, and the second term is v naught x, which has no t. So we need to do each of these individually. For the first one, when you take an integral of something which is linear in t, you're going to get a t squared, and then you're going to need to put a 1/2 out front to compensate for the 2 when you take the derivative. That's 1/2 axt squared. And then again here we have just taking the integral of a constant value just throws a t times the constant. And then we also have to specify that we're evaluating this at 0 and at the upper limit of t. Of course, setting those two limits is going to be easy because when I set t, I just get a t here and a t here. And if I set t equals 0 here, I get 0 here and 0 here. And that's my final answer for the integral of the left side. So now I want to combine these two expressions. They're equal to each other. Remember, there was an equality in here. So I'm going to set these two equal and then just solve for x of t. And there's my final answer. So this is the second kinematic equation, and it tells me the position as a function of time. It requires more information than the velocity one does. It requires the time, it requires the initial velocity, and it also requires the acceleration, but it also requires the initial position. That's basically this initial position comes from doing this integral and having to set this unknown constant because these were definite integrals, so we had this constant that we had to add on. So those are the two independent kinematic equations. Now, and for my money, these are the two things that you really need to know, and you can solve any one-dimensional motion problem as long as the acceleration is constant using just these two. But there is a way to get a third equation, which is a combination of both of these, which I'm also going to give you now. You don't necessarily need this equation to solve problems, but it can be very convenient to have this equation to solve problems. And essentially the key here is to look at what both of these equations have in common, and that is that this time. There's an unknown time which is you say I want to know the position and velocity after 3 seconds, after 5 seconds. But because it exists in both these equations, we can actually solve for it and eliminate it and get a new equation which doesn't have any time, and that can be a very convenient thing. So that's what I'm going to show you how to do next. So here are our two kinematic equations, and remember the thing that I want to try to do is eliminate the time t between them. So I'll get a single equation at the end which doesn't have time in it. So if you imagine trying to do this, first you're going to solve for t in one of these two and plug it into the other one. If you tried to solve for t in this equation, it would be a little bit of a headache because there's a t squared and a t. You'd have to use the quadratic formula to get that t and plug it in down here. It's not so hard to do that, but it is a little bit of more work than I think we need to do because down here we can just solve for this t and put it in here and there. That requires us to square it instead of having an ugly square root from the quadratic formula, but for my money it's easier to solve this guy and plug in to that. So that's what I'm going to try to do. So first I'm going to bring that v0x to the other side, and now I'm just going to divide by the acceleration. And I've solved for t out of that equation. The next step is to take that t and plug it in right here and right there, which looks like that. Next step is to distribute this square into the parentheses. I get something like that. Starting to get some cancellations. I'm going to have a cancellation between one power of acceleration on the bottom and that power of acceleration right there. So it looks like the next thing I'm going to want to do is multiply this guy times a half, multiply this guy times v0x. That gives me that, and you can see that I've also got some more nice cancellations here. These two terms are both only over the acceleration, so I'm going to be able to combine them. But further, I have a minus vxt right here, v0x, and a positive vxt v0x here, so those two terms are going to go away. I have another two similar terms, minus v0x squared and a positive 1/2 v0x squared. So I have a minus 1 and a positive 1/2, so that's going to give me a minus 1/2 in the end. So the next line I'm going to write is doing that as well as putting everything over the acceleration. Now to clean this up and make it look like the final formula, I want to move this x naught over way to the other side. Looks like that, and then let's multiply times ax and multiply times a half to get those guys over here and to get no fractions anywhere, which gives me that. So that's a nice form of this equation because it just shows that we have a change in the position times 2 times the acceleration is equal to a change in the square of the velocity. So I'm just going to put in a few more notational things to try to make this guy and this guy a little simpler. I'm going to call the change in position just delta x. I'm going to call the Vx at some time t the final velocity, and Vx at the initial time Vi. And my final third kinematic equation looks like this. 2a delta x times equals Vf squared minus Vi squared. Again, I want to emphasize that this is not a third independent kinematic equation. There's no extra information that is required to get this that you can't get from the other two. But if you're not giving time in a problem and you need to find one of the variables, it's common that this will be a simpler approach than going through using the other two. Now, I don't really like memorizing extra equations. I like to memorize as few equations as possible, so I don't usually memorize this equation. I usually just do 2 steps to solve problems like this. But if you want, you can memorize this equation and get simpler answers to some specific kinds of problems. Great, thanks everyone for watching. This has been one-dimensional constant acceleration and the kinematic equations.